Good day, ladies and gentlemen. This is the pre-prac video for experiment 4, which is the experiment using infrared spectroscopy. So in this experiment we are going to calculate the force constant of a number of carbonyl bonds. So you are going to look at a number of different compounds as listed in your practical manual: acetone, cyclohexanone, acetic acid anhydride, methyl acetate, acetophenone and benzaldehyde. So the first thing that I want you to do, and please do this before you do the practical, before you come to the lab, is to find the line drawings of these compounds. So for example, acetone looks like that, methyl acetate looks like that. Okay, so once you've done that, you will notice that these molecules all have one thing in common, and that is that they have a carbonyl group. However, they differ in terms of their R groups surrounding the carbonyl group. So a little bit of background with regards to infrared spectroscopy and infrared radiation. Infrared radiation excites vibrations in molecules. So atoms start vibrating in their bonds in the molecule when you irradiate the molecule with infrared radiation. So we are specifically interested in this practical in the vibration of the carbonyl bond. So you can imagine your carbon and your oxygen atom being connected by a spring. And remember, when we talk about vibration, we assume that spring to be represented by what we call a force constant, K. And the higher the force constant, K, the stiffer the spring. So the larger K, the stiffer the spring. And this is what we want to calculate in this experiment, the stiffness of that bond when it vibrates. So how easily does it vibrate? The stiffer the spring, the more difficult it is for that bond to vibrate. And you'll find that these R groups affect the vibration of the bond. For example, if you have two very large R groups attached to the carbonyl group, that atom or that carbonyl group will vibrate differently compared to a molecule where you have two smaller groups attached to the carbonyl group. So this is the type of interpretation that I want from you once you have the force constant. So you'll get a force constant for this molecule, a force constant for that molecule, compare the values and then interpret them in terms of the shape or the functional groups, the R groups in the molecule. So the next thing that I want to ask you to do before you come to the lab is to answer this question: so at what wave number do you expect, sorry guys, I can't spell expect, the carbonyl stretch? So the stretching wave number or stretching frequency, if you want to work with frequencies. So you can consult Mr. Google to find that information. You can also ask Mr. Google to help you with these line drawings, because that will tell you where in the spectrum you're going to find the information that you're looking for. So maybe try and find a value in wave numbers, because our spectrum is going to be measured in wave numbers. So you're going to measure different spectra, one for each of your molecules. So let's say that is our acetone spectrum, and this is our methyl acetate spectrum. So you measure intensity versus wave number, the IR spectrum of each of these compounds. And in your spectrum you are going to see the number of peaks, looking like that. And this one will look a bit different. And once you know which region to look at, you will then isolate the specific peak that corresponds to the carbonyl stretch. So let's say Google told you to look in, let's hypothetically say this region. Then you will know for methyl acetate that's your carbonyl stretch, and for acetone that peak corresponds to your carbonyl stretch. So you'll notice that the carbonyl stretch doesn't occur at the same position for each of these compounds. It falls within a specific region. And the reason for that is because the other R groups in the molecule affect the stiffness of the spring. So you read off the wave number for the carbonyl peak from the spectrum for each of your molecules. And once you have that information, you can use that to calculate the force constant K for that molecule. So if you look at the equation in your practical manual, the frequency for a harmonic oscillator, remember we're talking about oscillation, something vibrating, is given by that expression. Now this is a symbol you may not have seen before. That is the Greek symbol mu, which is known as the reduced mass, which you can calculate using that expression. And in this case, M1 is the mass of the oxygen atom, M2 is the mass of the carbon atom in the carbonyl group. So you can determine these using the ammo units in the data sheet. But remember, you read off wave number, not frequency, in your spectrum. But remember, wave number is frequency divided by C. So we can just write that equation in terms of wave number just by dividing it by C. So you can get the reduced mass, you have the wave number, so you can get the force constant for each of these molecules that you have measured. So you can get the force constant for each of your compounds, so the force constant for acetone, force constant for methyl acetate, and all the other compounds in the series. And then the questions ask you to tabulate the frequencies from the spectrums, calculate the force constant, and then also compare your values to that of carbon monoxide, and then comment on the differences, possible differences, and then lastly discuss possible reasons or interpret these frequencies and why they could be different for the different compounds in terms of their molecular and electronic structures. So this is where the R groups come into play. So look at the line drawings of the structures and see if you can interpret it in terms of these R groups. Why are some of the springs stiffer than others? Okay, so that is basically a summary of the practical experiment 4.